Hello and welcome everyone to a new lesson in ADAS-Imagine and remote sensing techniques. And today I would like to show you how to calculate manually the normalized differential vegetation index using ADAS-Imagine and some ETM plus data. First of all, we have to make sure that we have the raw data for calculating the NDVI. So as I have said, we will download them from the landsat or the Earth Science Data Interface page from the Global Land Cover Facilities. You can find them using the hyperlink to landcover.org. And I will use today some data sets from Mongolia again. And so we have a summer scene here, which is provided by the USGS. I'll download them. And due to the fact that you should probably know that the NDVI is calculated using the bands number 4, so the near infrared, and the band number 3 for the red, or the information of red reflectance, to calculate the NDVI. So therefore we will need these two bands. So there's band number 3, and there, wait a second, just download it. And there's band number 4. Download them both, and wait a second. As you can see here, I have already depressed or extracted the data from the archive, but there's another thing we need for calculation of the NDVI, and these are some kind of statistical values or apparature, I don't know the English word for that, values on how the sensors are measuring the data. And this is given by the MET file, so also download this please to your working directory. So this is probably the NDVI calculation directory, and yeah, just have a look in that. So we will go to the folder. Open this MET file with an editor of your choice, and as you can see here, we have some kind of really general data. So it's a Landsat 7 satellite system, and the sensor is ETM plus. You have the acquisition date, the path, and the row values, and also some kind of locational values. So the degrees of the centers and the corners. Then you have some file names and also the projection information. But what is really interesting for our usage today is the sun values, so the sun azimuth and the sun elevation, and also the values of the minimum maximum radiances each band or each sensor or band of the sensor can measure. So that you will have some values over here for each band 1, and there's also some kind of minimum maximum pixel values. And maybe you can remember that the Landsat data or the raw data we are using we can see here. So just present you the band number 4, and as you can see here, fit image to window, you can see a lot of white and black pixels and also gray ones. And what is each value saying? It's just a digital number, and this is a file pixel value. So you have the restriction that it should be between 1 and 255 due to the fact that it's stored in a 16 or 8-bit unsigned format, and the 0 values are showing that there's no information available, so it wasn't measured. So this we need to keep in mind. So if you're calculating the NDVI manually, and I will show you how to do that using the modeler in ADAS-Imagine, you have to transform these digital numbers to radiances. And due to the fact that we have a minimum maximum file pixel value of 1 and 255 and minimum and maximum possible measured radiances at the sensor given by the MET file, we can transform using a linear approach these values or the digital number values to radiances. And if you're just googling the problem on how to calculate radiances or digital numbers to radiances, you will surely come across this formula. So it says you will have a minimum, maximum, or maximum, minimum possible measured value in the scene. Then you have the given minimum, maximum digital numbers in the scene. Let me get it right. The spatial radiances, yes, and then you are using this as a slope of this linear function. Because if you're trying to convert these, I will probably show you in a short sketch this. Let me just stop for a second. See you soon. So let us look on this short sketch. So we have the digital numbers on the x-axis and the radians on the y-axis, and we are interested in a transformation, in a linear transformation from these values 1 and 255 to radiances. So what we need therefore are minimum and maximum values of the radians. So let us go to the MET file and just search for the values of the band number 3. So you're having a maximum band or a maximum value of radiances for the band of radians for the band number 3 given by the value 234.4. So go here, paste it. This is the maximum value. And the minimum value is -5. So once again, go here, paste it. And due to the fact that we are having a given starting point of this line, oh, please go ahead. So the starting point is somewhere here, and the end point is up here. You can transform easily each value, like this one here, to a given to a radiance value, which is probably over here. So let me assume this is 117. Oh, what is going wrong here? So this is 117, which is probably some value on the radiance, like, I don't know, like, let's suggest, oh, wrong decision. Oh, something about maybe 90. And this is the thing we need to do now. So we need the slope of this line, and we need the starting point and the end points, which were given by the MET file, and we will use this information in the modeler to calculate the radians from each band, like the fourth band and the third band. So first of all, we need the modeler, and as you may already or still know, go to this one, modeler, model maker, and for the modeler we need an input, a process, and output. Very simple. So we will connect these three elements, and the input is more or less one of the raw datas. So in our case now, it's the third band now. Okay, go ahead, declare integer, that's fine for me, everything is still okay. So what is the process behind that? So we are trying to make a ratio, and we will use this ratio to multiply it with another value, and that's it, I think. So probably once more check with the formula. So this is a ratio. This is our digital number. So the quantized calibrated pixel value in digital numbers given. Then we have to subtract the minimum value, which is possible in our scene, which is normally 1, and we have to add this minimum possible value in the radiances. So first of all, let's go to this ratio. So it's L max minus L min. Go again to this file. So L max is For the band number 3, it's 234.4. So this minus this divided by, go once more to this, qcol max minus qcol min, and you can recheck it on the MET file, but it normally should be. It depends on no, it does not depend. So in ETM plus you can be sure that it's 1 and 255. So it's 255 and 1, and this is 255. No, wrong keystroke. Come on. There we are. So it's 255 minus 1. So this is the first ratio. And then we have to multiply it with the digital number in the scene or in the band minus our minimum possible value, which is 1. And this is still we have to add the possible minimum measured value in the scene, which is in our case minus 5 here. So given this is the calculation we need to use. So we'll just add some braces over here. So this should be the calculation, and we will press OK. And due to the fact that we are calculating a ratio and we are going away from this 8-bit unsigned values, we have to make sure that the file name, that the possible data type is different. So I will just make radians, this is band3.img. That's fine for me in the moment. And the data type isn't anymore unsigned 8-bit. You are not possible to store ratios in that value. So we will have to change this to float signal, and this should be fine. So float double is much more space on your hard disk. Float single should be fine for our case. And you can probably go ahead and using this calculation, and we'll just try to run it as it is. Maybe we will get some problems with the 0 values in our scene, but as you can see here, everything is working fine. The radiances are calculated. I will go ahead and check the result in a new viewer. So go ahead, file, open, raster layer, please. Go to the working directory. And this is radiances band 3, fit image terminal. And as you can see, there's not so much difference between both of these pictures. I was using the band number 4. Go ahead, take another viewer. Also use file or raster opener. This is given as TIFF. Band number 3 and fit image terminal. As you can see, there's no real difference between the two, but this is okay because we just transformed it linearly. So if you're changing contrast in this way, you're not changing the inner proportions of digital numbers, and you're not changing proportion of radiances to the surrounding. But we need to make sure that there's a radiance given. So as you can see here, there's a file pixel of 52 in this case, and by linking both viewers geographically, you can check both values in both scenes. So it's 17 in this and 11.7 in the other scene. So now we have calculated the radiances given by the band number 3. We have to make sure that we are also calculating this for the band number 4. So go ahead, change this model to band number 4, go into calculation scheme, check the values for the bands. So in this case, the maximum value has changed and also the minimum value has changed. So we will use this on our and the minimum value is minus 5.1. So there we go. And as you can see, the used input has already changed here. So this is fine. Change the name here again, so it's band number 4, and go ahead in the calculation. So calculate this as well. And then we have both radiances, and we need to go further by converting these both information. So now we are calculating the radiances, and we need to transform these radiances to reflectances. So we need to make sure that we are changing the way or the energy that is coming from the sun is changed during the way onto the Earth's surface and back to the sensor. And we have to make sure that we are using the information of the atmosphere and also on the day of the year, so the Earth is not turning on a circle around the sun. It's more elliptical, and so the energy which is given by a beam of light is changing over the year, and also over the inclination of the sun above the Earth's surface. So we need this information to calculate the real reflectances. So if you're looking onto the internet how to calculate or how to transform radiance values to reflectance values, you will surely come across the Landsat handbook, which is which is a great handbook for getting some information on how to process Landsat data. And you will have this formula given here, which is said that you can calculate the reflectance using pi or p 3.14 and the radiance at the sensor, then a given distance in astronomical units from the Earth to the Sun, square this, and the distance you have to know is depends on the Julian date of the year, so we need the date of the year. Radiances we have already calculated. P we don't have to calculate this. And then we have in the lower part of this ratio is the mean solar exoatmospheric irradiances, which is some kind of buffer value on how to decrease the radiance at the sensor in a given band. So you will have these values over here. And the last one is the cosine of the solar zenith angle in degrees. So this is bothering me a little bit because look on some kind of on a definition on the solar zenith angle. So as you can see here, you have a solar zenith angle of 0 degrees if the sun is in zenith. So, and if you're calculating this, then you have nearly a cosine of that of about 1. So just look on the curve of the cosine. So if you have if you are having the sun in the near to the azimuth of 90 degrees, or near on the highest part, then the lower part of this ratio will increase, probably go to 1. If the sun is near at the horizon, so it should be the case when the solar zenith angle is increased up to 90 degrees, then the cosine is nearly 0. Which means that the cosine or this low value will increase the reflectance, due to the fact that dividing by half means doubling the incoming value, which is the radiance in our case. So there's a little struggle around these both definitions. So I think that we need to use the real given value in the MAT file, which is probably here the elevation. And in this case, it's 50 degrees, which is quite useful due to the fact that we are in the northern hemisphere and it's a little bit after the 21st of June, and 50 degrees is much more than 45 degrees, which is quite fine in our area. And so we need this value for the calculation of the cosine. So we'll just copy and paste it into our model and go in here, and as you may know, we need this modeler to calculate the reflectance. So first of all, we need as an input not the raw data. We need the calculated radiances. So we need the radiances in band number 3 as the input data. So it's given as a float value. Just go again to the formula where it is. So it's here, and now we need P. We'll just leave this open for reasons. So we need P 3.15, which is enough for reasons just to show you. Then we need the radiances, which are stored in the radiances band 3. Then we need to multiply this value by the given distance regarding a Julian day of the year. So go again to the MAT file, and you can see there the acquisition date. The acquisition date is the 20th of August 2001, and you can also find in Landsat handbook this Excel sheet. So we have astronomical units for every day of the year. So we need the day of the year given by the 20th of August. So you can go again into the internet, search for these values. So 20th of August. August is up here. The 20th is the 232nd day. Yeah. So 232. Go again to the model. To the Excel file, 232. There's an astronomical distance of 1.011, and we need to square this. So go again, check for the I'll just make it like this. So keep it quite simple. So this is a squared astronomical distance, and we need to divide this by, go again here to the formula, the exoatmospheric irradiances values. So we have the band number 3, and this is more or less 1533. And we need to multiply this by the cosine of 50.7. So I think there we go. Rescale this, so it's reflectances band 3. Okay. And let's try whether this will work. So calculation is fine. Computing statistics is also going on. So let's prepare a new viewer to check the results. So we will open this. It's an IMG. And so we have the reflectances, and we should expect a value between 0 and 1 due to the fact that it's just converting the input to an output. So as you can see here, these are quite low values, and they are increasing by this. So due to the fact that the sun is not so much high in or the azimuth isn't so high, the values of reflectances are very low in this case. So this is the band number 3. We need to arrange this for the band number 4. So there's another input file, and there's also another value for this given, which is more or less 1039. The cosine is still the same, and also all the other parameters. So we use this reflectances band number 4. Go ahead, and there we are. Just calculate the model, and then we can go to the informative part, like calculate the NDVI. So there's a lot of pre-processing in this model. But normally all the software packages you can buy and you will probably use on your scientific work will have some kind of tool to automatically calculate the NDVI. So this is finished now, and what we will need to do is just keep in mind the original formula, which is NER minus rad divided by NER plus rad. So it's band number 4 minus band number 3 divided by band number 4 plus band number 3. So for the calculation of the NDVI, we will just use the old model. We need to add another input data, because we are now mixing up two different rasters. First of all, the reflectances is in the band number 4. There we go. Then we are having another input, the reflectances is in band number 3. So use this. And the model behind that is more or less given by this formula, NIR minus rad divided by NIR plus rad. So we just have to minus rad. The rad is given by band number 3, and we will just some brackets, and then the same into the other direction. So just summing up these both rasters, and this is more or less the NDVI. So use this. We will serve it here in a new raster, which is the NDVI manually. Float single is fine as well, and go ahead and check it out. So I think this will take some time. So the calculation is finished now, and as you can see here, we have the manually given result of our calculation. So water bodies are marked as with red, or no, not with red, but with black pixels here, and you can make an inquiry of the pixel location, and as you can see here, they are really small values. An NDVI given of 1 indicates healthy vegetation, which is photosynthetic active, or photosynthetic, which is active and growing, and it's green. And then you're also having this grayish ones. There's no vegetation given, and as you can see here, the floodplain is full of vegetation, or active vegetation, and also the slopes are photosynthetically active, due to the fact that you are having some forests over there. And as I've said, you can calculate this values automatically given by some tools here. So spectral enhancement, indices. There's this NDVI calculation, but behind this NDVI calculation works just another model. So let me show you. File open and vegetation NDVI, and as you can see here, you have an input raster, which is a layer stack, and which is a layer stack. And no, what I'm doing there, I'm a little bit confused, sorry, it's late. So we have the input raster, which is a layer stack called linear in this case, and this layer stack have 4 or 2 layers, the band number 4 and the band number 3. You can just create a new layer stack out of the bands number 4 and 3, just a 2-layered layer stack. Input it here, so this is the infrared minus the near infrared minus the visible red, then the near infrared plus the visible red. Then they are storing some kind of just temporary rasters. Then they're doing either differentiation, and they are calculating the ratio between these both. And the ratio is stored in another temporary raster, and then they are calculating digital numbers again out of this data to decrease the file size. But I've just deleted these both parts and calculated it and automatically done raster. So I was storing this raster, and I would like to show you the differences between these both. So just go ahead, there's the NDVI manually, open another viewer. If you would like to do it as well, just check out my videos, how to calculate the layer stack, how to use the raster calculator or the modeler for calculating sums and all like that. And just go here into this, and as you can see here, it looks quite similar to this. So to get an idea about the differences between these both values, you can also use, of course, the inquiry cursor to check the values here, so they are quite similar. Also we have minus or negative values in the lake, but how great or how big are the differences between these both approaches? Because the manual calculation, as you have seen, is quite time consuming. And you just want to have an idea about the photosynthetic, what a different word, a difficult word, just about the active vegetation in your area. And just for this, maybe the automatic approaches are much easier to compute, of course, as we have probably seen. So we will go ahead into another modeler, and we will use now the input, the automatically raster and the manually created raster as an input, and we will calculate just the difference between these both. Oh no, something hasn't worked here. There we go. So it's this one. And we'll just create the differences between both of them. Store it as the diff.img. Okay. And this is our floating raster, delete if exists. I've also already created one. Sorry for that. So I'll calculate this. Just close all these other things here just to tidy up a little bit the desktop. And no. Thank you. And I don't need ArcMap in the moment. So no. And there we are done. We'll open a new viewer. Open the raster, look at the difference image, and what we can see here, there are a lot of differences, but how big are they? As you can see, they are more or less nearly stable around -2. So go again, check the information, the histogram. As you can see, there's a little shift in the information, so it's about -0.2. So the automatic given value is a little bit higher than the manually given value, and especially if you're looking here on these slopes. So these are northern exposed slopes, and they are negatively given in that area. So this is just an idea. So there is first of all, there is a difference between the automatically and the manually done approach. Second of all, do you care about? This question you have to ask yourself, because just look on the profile here. I'll just make a spatial profile. This looks spectacular. Whitish, blackish scenes here, and look at that. It's nearly nothing. Nearly no difference between these pixels. And so, just to make sure that if you just want to have an idea about the vegetational coverage and the activity of the coverage, go ahead with the automatic approach. If you're using, or if you're making some comparisons between different time steps and so on, you should not, I repeat that, you should not use the automatic approach because of the inclinations of the sun, the differences in the distances of Earth and Sun, and so on. So these are both some things you have to keep in mind. If you just want to have an idea, use the automatic one. I would do it like that. If you're using it for comparison between different time steps and different systems, use the manual approach. Thank you very much for watching. Enjoy my video channel and see you soon.